think should be live. Are we live? Twitch. Oh, it's been a while, so yeah, I guess I'm live. It's show some ads. It's weird having to watch my own ads, so but I just want to see, make sure the audio and stuff is working fine. We can hear, everybody can hear me, kind of thing. I think so, huh? It's just like layered on top. What's the audio like? Okay, that seems fine. Alright, cool. So let's get this going. Yeah, we're going to be going through OSSU. I've done a little bit. And then I've started on... So I did this, right, like, I don't know, like a year and a half ago, something. Started on the core thing, systematic, did a little bit, and then kind of just fell off. So today, probably be like mostly just like revisiting the stuff and yeah, I don't know, revisiting it and just like walk through the code until we get to, I believe it's week 4 or 5 where I left off. So that's the plan. Yeah, let's just say, do I have a Discord? Yeah, I was gonna announce here if anybody's coming. General, I think I announced this when I'm coming, yeah. Okay, going live. Starting today. Daily streams. Let's go. And then I do need the stream URL. Okay. Alright, if anybody wants to hop on, they can. But we are gonna get this rolling. Just have that go in there. Mute myself. I believe there's like... Sorry, I'm trying to get my Twitch studio thing going. Studio.twitch.tv. Is that how that works? Yeah, I've got Safari here. Twitch stream settings. Because there's a way for me to like manage the streams or something like that. Stream summary. I mean, this is live right now. Stream manager. That's what I want. Sure. Yeah, that's what I want. So we can sort of keep track here what's going on. So that's OBS. I think OBS can chill out there. Let's get the music back in. You may not be able to hear the music, so in that case, bring your own. Then we have this one. This can stay here too. Alright. Alright. How does this work? It's been a while since I... I think... what is that? Activity feed. Collaboration. No, I don't want any of that. Chat. I mean, it's probably going to be nobody for the first couple of weeks anyway. That's how it was last time. It was just me working through. Alright, so let's do this. So what did I do last time? I did have github.com. So this thing here, yeah, like 5 months ago, I played with started it 2 years ago, and then the core I think was a year ago, and then kind of stuck there. So we're gonna go through. Yeah, I'm in the core systematic program design. So it looks like I got up to week 3. Is that right? Okay, I'm going around circles now. Yeah, I think these notes are hard to keep track of too. Yeah, okay, that's fine. This playlist. Okay. Work through week 1 to 6 as given in the course overview. Watch the video, do the exercises, and solve the problems from the problem bank. So week 6 and then 6B onwards, do that, and after you do all of that, that's fine. Okay. Kind of don't wanna. Do I watch the videos again? I don't know. I'm trying to think. So recipes, I remember recipes. Checklist is one of the things. Yeah, okay, this is fine. Yeah, I remember the design recipes. I think I should just do it, like, because it's been a while. It's to start from scratch, like from today. Okay, what do we need? So we need. So what was this? Starters. Expressions. So it's gonna open up like a racket file. I don't remember if these have the answers, so we're just gonna go. Just download it, I guess. That's fine. Clone starters. What's in final? What's? Can I do racket? Do that. Like I know I got Doctor Racket. DR, yeah. I don't know if I could do DR Racket. Does it have a CLI? No, okay. Alright, fine. Sure. Okay, this white mode is bright. Okay, so there must be a way to do dark mode. Bro, like, what was the... Does it have settings? Preferences? Oh, there we go. Editing, yeah, we want... white on black, yeah, there we go. Actually, this looks better. No, it's more readable. Okay, cool, that's fine. So got beginner student language. What is all this? Primitives. Alright. How to design functions, how to design data. Okay, it might just be like me just going through watching the videos, man, because I think it just has to be done. Alright, so recommended link is through this. So I think I know how to log into this. Yeah, let me see if I can log in here. Systematic program design. EDX. Okay. Okay, so I've logged into the recommended. I wish I could turn this like dark or something. That'd be cool, but pretty bright. Do they have dark mode somewhere? Ooh, okay. Right. Okay, so that's not what we want. I wanna know hang on 2 seconds. Okay, alright, that's fine. Gonna have to do that. Okay, cool. That's fine, I guess. Alright, so. Right, audio stop playing, which is not what I want. Okay, that's fine. Alright, cool. So let's go through this one, which is why I'm here. Okay. Set a goal, intense. We're gonna be doing this for real now, like every day. Introduction, I've kind of been through it before. Syllabus, that's fine. Beginning student language. Alright, we can start from there. I need to figure out how to do this stuff. Notes. So I think this was just like my notes, right? As I went through. Okay, yeah, let's just do that. The first module is for for people who've already programmed, which includes me now. This may seem too easy, but be careful. Okay, that's fine. Man, this is I don't have dark mode, bro. This is crazy. Okay, who we got? We got Naz in the chat. What's up, Naz? Either human or your bot, because I'm not expecting anybody to be here anyway. For now, so we're just getting started. Okay. Approximately 5 to 8 hours. Yeah, if we can rock this today, that'd be nice. Okay, expressions. So to start with that. I don't think these links work anymore. Yeah, okay. Alright, I'm just gonna 2x and just listen to this.
So as I said in the introduction, we're going to design some great programs in this course. Some games, some animations, some information visualization, some web programs, really great stuff.
Some games and stuff. Okay.
And in the same way, we've got to learn some basic building blocks before we can build these great programs. So that's what we're going to do for the next few videos, is learn the basic building blocks out of which we're going to build bigger programs. I'm going to try to do it quickly because it isn't that exciting, but we're going to try not to do it too quickly.
Yeah, so whoever's watching, like, you can just have it in the background because this is gonna be long videos. It's me just like learning stuff, struggling. It's gonna be fun. It's gonna be fun. The fun will happen like a year from now when we get to the good stuff, I think. But yeah. I think I've done this one already. Teaching, yeah, beginning student.
And in the bottom window, we have what's called a value. And the way racket is working is we give it expressions, and it evaluates the expression to produce the value. The expressions could be more complicated. For example, we could say plus 3 times 2 3. And we can run that program, and no surprise, it produces 1. We can make it expressions that are even more complicated than that, or use other primitive operators. Here we'll just divide 12 by times 2, 3, and unsurprisingly, that let's do it. So what we've seen so far is the
Okay.
open
I think we're
parentheses,
not do
primitive
this.
operator like plus or times or slash, and then any number of other expressions followed by a curly parenthesis.
Yeah, okay, this is
Expressions
hard
can
to
be actual
do.
values, so numbers themselves are expressions. Let me show you another thing we can do. We can take all of this, and if we say a racket, comment that out with semicolons. And it'll put a semicolon in front of each of those
Can
lines.
I?
And what that tells racket is that now we should ignore everything on a line after the first semicolon. So if I run this program now, as far as racket's concerned, there's no expressions in there at all, so there's no values at all. Let me tell you about two more primitive operations on numbers, and then I'll ask you to do an exercise. The first one is SQR, we call it square. And if I take square of 3, and I'll show you another one here at the same time, square root of 16, and I'll run these two. And what you're seeing is that square squares the number, and square root produces the square root of the number. Okay, we've seen how to form expressions.
Yeah, okay, so just like, here's what we want to do, and then, can I make this bigger? Like, really? Editor, increase font to 33. Isn't that what we have? Oh man, this is like real slow. Okay, that's fine. Okay, so you kind of do it like, it's like 3 times 2, sort of like that. That becomes 6, 6. Okay. So you can do additions, divisions, and then if you want to do like 6 times 6, I can go 6 plus, I guess, something like that. Oh. Okay. Expected function after the parentheses found a number. Okay, what did I mess up? Oh, you need a space. Okay. Yeah, okay, so you can do that. Addition, I mean, I guess that would just be a 1. Division. Yeah, okay, so you can do things like that, which is cool. Alright, and then square of 3, obviously that's gonna be a 9. Square root you can do. Oh, 16 is gonna be 4. Yeah, okay.
And we've seen a number of primitives that operate on numbers, primitive of plus and times and divide and minus.
That's fine.
What else do we
Write a expression that will find it's the square root of, I really like square root of, so like 3 and 3. Okay, so you gotta go up. And this is another square, like this. Man, these parentheses are gonna kill me. So, how do people keep track of that stuff? Yeah, that makes sense. I wish I could copy this, but whatever.
In the next video, we're going to look at the more precise rules that Racket uses for. I know that I need to square 3. It's pretty much the hardest math we're going to do. That's because you need to understand that. Why is that? Well, you may know that the square root of 2 is an irrational number, and what it means is exact. And you may see numbers like that crop up. Don't worry about it.
Square root? Oh, of course, we just have square, right? So you can just do that. Square of 3, square of 4, and square root all of that. Okay, that's fine. Yeah, okay. Okay, cool. So, if you see, what does that mean? This is, yeah, these all make sense. Okay, I think we just skip through these. So, like, So from the average of 4, 6 and that, you can do add them all up, divided by 3. Add -8. Oh, you just do the thing. Oh, to me this is clearer as 3 numbers, but like same thing. Please, okay, whatever. Evaluation.
In
No.
the last video, we learned how to write expressions that operate on numbers. That video should have given you a pretty good sense of how to write those expressions. In this video, we're going to look in more detail at the rules Racket uses to evaluate those expressions. Now, you may find it a little pedantic to talk about the precise rules for evaluating an expression like +1, 2. And if all programs were that short,
I'm actually curious how it sounds like on the streams.
you'd be right. But here's something to consider. The Chevy Volt has 10 million lines of source code in it. 10 million lines of source code in a car.
I'm waiting for the 10-minute line part. Kind of. You can kind of hear it. Okay, that's fine.
So programs get quite big. If that was a program written in the beginning student language, it would have many more than 10 million expressions in it. And it turns out that in order to be able to understand big programs, we really need to understand the detailed rules by which expressions get evaluated. We won't always need to think in terms of those rules, but we do need to have them to fall back on. So that's what we're going to look at in this video. Here's the expression that I'd like to work with. And if I just run this, I'll get the value 14. What I want to do, though, is look at the detailed step-by-step process that Racket uses when it evaluates this expression that results in 14. Before I do that, I want to introduce an additional bit of terminology here. We're going to say that an expression, like this one, because it starts with an open parenthesis and then the name of a primitive operation, is called a primitive call or call to a primitive. And in a primitive call, we're going to say that this is the operator. And in a primitive call, we're going to say that all of these expressions that follow the operator, in this case there's 3 of them, are the operands. And of course we could do the same thing because there's another primitive call sitting right here. And inside that primitive call, that's the operator. And those are the operands. And I could do the same thing over here. So that's a bit of terminology. Now let's look at the step-by-step process that takes that expression and ends up producing the value 14. Well, the first thing that happens is Racket is asked to evaluate this entire expression. And it sees that it's a primitive call because it starts with an open parenthesis and a primitive operator. So the rule for evaluating a primitive call is that first all of the operands need to be reduced to values. Well, this operand, the first one, already is a value. So no evaluation work is going to be required there. It already is a value. But this operand is an expression. It's not a value.
So it's like
So what is gonna be required there?
operands, operators.
Let's look at that. Well, this whole thing is a primitive call because it starts with a parenthesis and a primitive operator. So let's look at its operands. Well, that first operand is already a value, so no work required there. And that second operand is already a value, so no work required there. So at this point, the 2 operands in this primitive call have been reduced to values. And so this multiplication can happen. And this whole thing is just going to become...
Like, I don't know if these words are like
So we'll say that the
specific
first step in the evaluation,
to
this whole expression becomes this. Now, I've left some extra space
general
here because we
concepts,
wanna
or
make sure
if
that things
it's
continue
just
to line up.
specific to
Here we
this
see that in the first
language.
evaluation step,
Because I haven't heard of
operand
these when I'm doing like
is
Ruby and
reduced to
stuff, right? That's what I have
Well, now we've
experience
reduced
with.
the first 2 operands to plus to values. We need to work on this third one. It's an expression now. It's not a value, so we need to work on it. Let's see. Open paren, name of primitive operation. This first operand here is not a value,
Yeah, that's
so we
fine.
need to reduce it. Let's see. Open paren, the name of primitive operation. This 3 values, so that plus itself can happen. Detailed step-by-step evaluation because we go left to right. All of the operands to that minus have to become values before the minus can proceed. That left to right, inside to outside intuition is an important way to understand the evaluation of expressions in the beginning student language. Now you've seen the first evaluation rule, the primification of that rule. That's one of the
Yeah, I
reasons
mean,
why we're
that,
using this
that
now.
makes sense, I
It
think.
lets us spend not very much time.
Left to right. Yeah, okay. Yeah, so evaluation happens left to right. So we said right. That's fine. Yeah, I don't want to be doing strings and images. Okay.
In this video, we're going to learn about strings, which are used to represent words and names, and images, quite quickly. Someone's name, and strings are values. So if we run a program with these 2 strings in it, the value of the strings is the strings themselves. So apple produces apple, and Ada produces Ada. Now what are some things we can do with strings? Well, one thing we can do with strings is put them together. So let's say we have 2 strings, Ada, which is someone's first name, and Lovelace, which is someone's last name. We can put them together like that. And if we run that, string append is an operation kind of like plus, but for strings.
String
Glues the
append.
2 strings together like that. And probably if it's somebody's name, we might want to put another space in there. And one way to do that is we would just add a third argument to string append that adds the extra space in there. And there we go, and then we get A like this. You might want to look up. She's very famous for computer science. In the 1840s, she wrote the first computer program ever written. It was written for a machine which at the time only existed on paper. The machine itself didn't run until quite recently, but she wrote the program in the 1840s. So that's one thing we can do with
Twitch
strings. We can add strings,
stream.
put strings together.
Okay, so
Let me just point out one little wrinkle about strings. This is a string. That is a string that happens to have the characters 1, 2, and 3 in it. And this is a number, 123. And they're not the same. So in particular, Okay, let me show you two more primitives on 5 characters. Well, sure enough.
So string length is a thing. One, two, three, four, five, six.
That's one thing we can do with string. There's another operation we have called substring. And substring is going to let us take out parts of a string. So if, for example, we have a string like caribou, substring lets us take out parts of the string. Let me just give you an example here. If I say caribou 2 and 4, that's going to mean take out all the characters from 2 to 4. Give us just those characters. Now that's RI. And the question is, why is that RI? Well, there's a funny little trick here that computer scientists have played on the world, which is to use something called zero-based indexing. In order to understand zero-based indexing, the way I always do it is I make myself a string that looks like this. I make a little string that's 0, 1, 2, 3, 4, 5, 6, 7, 8. That's probably long enough for now. Okay? And what zero-based indexing means is it means that for substring, if we operate in this string here, 0, 1, 2, 3, 4, 5, 6, 7, 8, and we go from 2 to 4, it means start at character number 2 in zero-based indexing, and go right up to, but not including character number 4, in zero-based indexing. So again, if you take that, what are called off-by-1 errors because they confuse the zero-based indexing, make a mistake, design method.
Okay, that's fine. I mean, all of these are sort of basics here, right? That's fine. Strings and images.
Okay, that's some basics about strings. What I'd like to do now is go look at some basics about images. So what I'll do is I'll make a new tab. Dr. Racket has lots of different kinds of image functions. In order to tell it that we want to use the ones for this course, we're going to type at the top of this file, and any file in this course that uses image functions, require 2 HTTP image. And what this is telling Dr. Racket is it means we want to use the image functions that come from the second edition of the How to Design Programs book. It's a little bit of a mouthful, but you can just type that at the top of any file in which you use image functions. Now there's lots and lots of image primitives. Some of them make images. For example, the circle primitive. The first argument to circle is the radius in screen coordinates of pixels. The second argument to circle says whether the circle should be solid or an outline. And the third argument is a color. So that expression there produces that red circle. So we call the primitive circle, we get a red circle. And there's lots of similar shapes. Rectangle. Rectangle takes a width and a height. And it can take outline or solid, and it has different, we can try some of our other colors. There we go, we got a rectangle. And there's just a whole bunch of them. I'm not going to go through all of them right now. Another one that's quite useful, though, is called text. Text takes a string, for example, hello, and a font size like 24, and another color like orange. And it produces, this is now an image of the string hello in font size 24, color orange. So this is an image now, it's not a string.
Oh, you can have a text like that too. That's cool. Okay, so that's text coding crazy 24 green. Yeah, it's not bad. This is because it's outline mode. Okay, cool. That's fine. That's pretty cool, I guess.
So that's a bunch of useful primitives for making images. Make a circle with this one 20, and we'll make this one 30, and to make it pretty, we can change the colors too. There we go. So now what happens when I run that is I get this stack of the images. Above takes all of the images that it receives as arguments, and it stacks them one on top of another. So above is kind of a sort of version of string append for images. But since images can be arrayed in lots of different ways, there's lots of other functions. So in addition to above is, for example, beside. And if I run that, I get that shape. In addition to beside, there's a thing called overlay. Overlay. And if I run that, overlay stacks them on top of each other. There's lots
Okay, there's above. I think he said above, beside, and overlay. Overlay. Yeah, I guess I should probably go red. Red, yellow, green. Okay. Do the same thing here. But that's a bit too much. Okay, that's cool.
lots and lots of primitives that operate on images. And as you do homework exercises this week, you get a chance to look them up and play with them. But for example, there's functions that make ellipses and stars and triangles and things like that. And you can line images up and put them next to each other in different ways. But these are a good set of basic functions right here. Circle, rectangle, text, overlay, above, and beside.
Oh, so you make it like different sizes. That's cool.
Little exercise you can do here to test your understanding about.
Which image will produce the following? So besides, it's going to be side by side. And there's two things. We've got a square, and then you have a circle and triangle Yeah, this one. Right. Let's double check. Pretty simple stuff. Yeah, okay, makes sense. Yeah, I don't want to look at that. Create my own image. No, I don't want to do that. Let's just move on. Constants.
We've been learning about different kinds of values, numbers, strings, and images, and how to write expressions that operate on those values. In this video, we're going to look at something quite different. We're going to look at how to write constant definitions to give names to values so that we can use those values in different parts of the program. Constant definitions are more than just a convenience. We're going to see later in the course that they help us make programs that are easy for other people to read and easy for other people to change. And that those two properties, readability and changeability, are two of the most important properties a program can have.
Readability and changeability. I've heard that before,
So
but
that
it's
you can learn how to
good
write
to
constant
kind
definition to give names to a value that you use in other parts of the program. So let's imagine
yeah, I don't know how this will work with like AI coming in and stuff.
One thing we might want to do is give names to the width and height of the window. And the way we do that is we write open paren, define, and then some name, which we often put names of constants in uppercase, like this. And we might say that the window is 400 pixels wide, and maybe the window
400.
600 high. And that's two named constants. If we run this program just like this, we don't get any values out, because defining a constant doesn't produce a value. And now what I can do is I can write an expression, like this. And what happens is when Racket evaluates this, when it comes to evaluating the name of the defined constant, it's just going to use the constant's value there. So this will become 400. So the evaluation steps here would be times width will become 400. That's the first evaluation step. And the next evaluation step, height will evaluate to 600. At this point, all the arguments to times are values. So now we have 240,000.
That makes sense.
So the way to form a constant definition is have an open parenthesis, word define, a space, and then a name. And names typically include letters of the alphabet in upper and lowercase. They can also include numerical digits.
Name expressions like
they can include lots of other characters like exclamation mark and question mark and equals and things like that. Some languages are more restrictive about that. The beginning student language is fairly generous about that. You can't use parentheses or quotes at any time, though. The rules for evaluating a constant definition are when Racket encounters the constant definition, it evaluates the expression and uses the resulting value as the value of the name constant going forward. When evaluation encounters a name constant, the name constant simply evaluates to the value that the define associated with it. Let's look at another example. Let me get rid of all this now. Suppose in this same program, in my game program, what we have is an image of a cat going back and forth across the screen. Well, I might want to give a name to that image so I can use it in lots of places. So there's the cat. And what I'm going to do here is go to the second edition of the How to Design Programs book, which we use as the basis for material in this course. And they happen to have a little cat here.
There's a book. Can I access this book? ccs.neu.edu home. Not found. Book not found. Okay, I really want the image for cat. I think I had it in my other notes. Let me check. How do I? Can I control O? Yeah, okay. Downloads documents. Okay. Stream code. In my notes from like, oh no, like 4 months ago. I think they had it. Yeah. Control C. Yeah, so if you're new on the stream, basically, I've been through this before. 6 months ago, I'm going through it again. But I never completed it, so. Yeah, okay, so we can go define cat. It's interesting. So you can have images as a variable. That's interesting.
Copy this image.
I'll
come back over here and I'll just paste it right in here. And what's happening in Racket is remember that images are values.
And can I just go
so I can stick
cat?
that image right there in the program as an expression. Most languages won't let you do this, but it's quite convenient to be able to do it in BSL, so we're going to take advantage of that. So now I've got a cat, and I can make some expressions. So here, rotate is a primitive, and this says rotate the cat by -10 degrees. Here's another expression that would rotate the cat by 10 degrees. If we run this now, you see first expression produces the cat rotated this way, the second expression produces the cat rotated that way. And we might even want to give names to these, because remember I said that we can have an expression here after the constant name. So now I've given names to those two rotated cats. Oops.
Cat variable is not defined. Oh, because it's oh, variables like it's better to have in or best practice rather. Okay, cool. Define.
Different name. You can only define a given constant name one time. That's why it's called a constant name. It can't change. So I'll call those the R cat and the L cat. And there they are. So here you see that what Racket is letting us do is say define and a name and then an expression. That expression gets evaluated, and forevermore that value will be associated with the constant name. So we can use it in other places in the program.
Interesting. So then Does that get run when you define it? No, right? No, definite. And then I got to come down here and go cat, r cat, o cat, like that. This variable I1, what's I1? Oh, never mind, that's the old one. Okay. Yep, it's fine. Cool. Let's move on. Questions? No, we're not doing questions right now. Constant
Next, we have
definitions.
defined constants in
Part
beginning
2.
student language. As I said at the beginning of this video, we're going to see more and more how important this is. Really, this notion of defining name constants is going to have a big effect on making our programs comprehensible to other programmers and easy to change in the future.
Did we just go through this? I don't know what it is. Function definitions. Alright, there we go. Functions.
In this video, I'm going to talk about functions. Functions are the mechanism in the beginning student language that's going to let you write programs that produce a different value each time they run. Right now, our programs are always producing the same value. So functions are incredibly important and powerful, and they're going to form the bulk of our programs. But I think what you're going to see here in a few minutes is that in the beginning student language, functions are not too difficult to learn. We're starting to be able to build up some interesting results. For example, here, by using above and circle 3 times, I can write an expression which, when I run it, produces this little traffic light, or at least it's sort of like a North American traffic light, except that too many lights are on. But let's look at this expression a bit. It's easy to be bothered by the amount of redundancy in it. Notice that in this expression, all of these parts are unchanging. In the 3 calls to circle, these parts are unchanging. Only this part here is changing in each of the calls to circle. And it's easy to be worried, gosh, if programs get big, and a lot of them are sort of duplicated code like this, that seems needless. That seems like it's going to be cumbersome. And it would be cumbersome, and it is needless. There's a mechanism that's going to let us prevent that, called function definitions. So what are function definitions and how do they work? Well, you actually already understand a lot about function definitions. You just have to remember your grade school math, in which you learn that you could write mathematical functions like this. For example, here is f of x that equals 2 times x. And that means that f of 2 is 2 times 2 is 4, or f of 6 is 2 times 6 is 12. What's going on in these function definitions is that x, which is called the parameter, stands for the varying value, and then the rest of the function definition is the unchanging value, the 2 times in this case. And then the function can be used any number of times with a different value each time, or even sometimes it can be used with the same value as before. And each time, the parameter will take on the changing value, and you'll get the result of the function with that value. So how's this going to work for us? The beginning student language has a function definition mechanism. And it works like this. I'm going to write define, open paren, the name of a function. In our functions, we're not going to have to use single character names like x. I'm going to call this function bulb. And the name of a parameter, which in this case I'll call c. And then I'm going to write that the body of the function is circle, 40, solid, and then c. And what's going to happen here, just like in mathematical functions, is that the parameter c is going to stand for the changing value. And the body of the function is going to use that parameter in the place where it wants to use the changing value. And now I can show you how this function works. If I write open paren bulb and then say purple, this is a call to the function. Intuitively, you can think of it that the body of the function is evaluated with c taking on the value purple. In a minute, I'll show you the exact evaluation rule. But for now, you can think of it intuitively that way. Now that I have the bulb function, I can clean this up some. Let me just take this whole thing, and for now, I'll just comment it out. I'm going to get rid of this little purple, because that was just for demonstration. And I'll rewrite the original expression we had this way. And then when I run the program, I get the same result as before. Now this expression, at the end, is much more concise than the original expression. It reduces the duplication, and also by choosing a nice name here, by choosing the name bulb, I give the code a bit more meaning. I can now think of these as 3 bulbs on top of the other. And what we do now in a real program is we go ahead and completely get rid of this commented out stuff. And just because I think it looks better because these bulbs are one on top of the other, I would probably format this above that way. And now I've got something that's nice and concise, and it's clear for me to understand what it's doing.
Oh, interesting. Okay, I guess the next thing. So if I wanted to give it like the width, yeah. Okay. So if I say width and color, and we put a width there, and so it's going to be 10, 20, 30, red, yellow. Just like function params, I guess. Yeah, okay, it's fine. Above. I think above. What are the other ones? Above. Let's start overlay. Let's try overlay. Yeah, okay, cool. This is cool. Alright, functions. I mean, the technical terms, whatever, I forgot what it was calling it, but I mean, concept makes sense, so let's move on. Don't want to do that. Function definitions, part 2.
What I want to do now is the same thing we've done with all the other beginning student language constructs we've seen, which is to go over in a little bit more detail the rules for forming function definitions and function calls, and also the rules for evaluating function calls.
Okay, I will be right back. How do I pause streams now that Twitch TV streams? No, nah. Stream manager. I want to pause this stream for a bit. unstable. Alright, here's what I'm seeing. Where'd he go? What the? Weird. I don't know where the other thing went on my screen. What the? Guess I closed it. Twitch. I have no idea. I'm gonna go to stream summary, stream manager. I guess it has to happen from studio mode. Transition. No, okay, I'm just gonna mute myself. I'll be back in like 2 minutes. Okay, I am back. If anybody's still here. Okay, what have we got? So we've been live for 45 minutes. It doesn't feel like 45 minutes, but keep going.
Before I get to those rules, I just want to show you something, which is where you can find all the rules for the BSL language. If you go to the course webpage and you scroll here to the languages tab, then this page has all the rules for the BSL language, including how to form all the kinds of expressions we've seen and the rules for evaluating them and so on. The rule for forming a function definition is simple. We start with open paren define because it's a definition. And then we have open paren and the name of the function, followed by the names of the parameters. In the example we have so far, we just have one parameter c, but we'll define other functions later that have more than one parameter. And then we close that paren. So this first part has open paren, the name of the function, the name of the parameters, and we close that paren. And then we always put it on a new line. We have an expression which forms the body of the function. So here's the example we've seen so far. Define, the name of the function is bulb, the parameter is c, and here's the body of the function. To form a function call expression, we put open paren, the name of a defined function, and then we put some number of expressions corresponding to the number of parameters the function has. So for our bulb function, which has a single parameter, we put a single expression after the bulb name. And those expressions are all called operands. To show you how the rules for evaluation related functions work, I'm going to first start by getting a somewhat simpler example. What I've got here is a call to bulb, where its argument, instead of already being a value, is going to be another call, a primitive call. And I'm also going to set up by putting the rules for evaluating functions and primitive calls here on the right. So let's see, we look at open paren bulb, and that tells us that we got a function call. So the rule for evaluating function call is to first reduce the operands to values. So now let's go look at the first operand. The first operand is open paren string append. So that's a primitive call. So we now look at the rules for evaluating a primitive call. And the first rule is to reduce operands to values again. Notice that the first rule for function calls and primitive calls is the same. You reduce the operands to values. Well, let's see, the string RE and the string D are both already values. So now we can apply the string append primitive. And the first full step in the evaluation is that we now have bulb with an operand of value red.
Yeah, I mean, this is sort
Now
of
going back to
basic
the function
stuff.
calls,
Look at
we have now
this.
reduced the first operand to a value, so we reduce all the operands to a value. Now we're going to replace the function call by the body of the function. So copy the body of the function down here. But in the body of the function, different steps that gets a red circle. So if you do your step-by-step evaluation exercises in the definitions window like this, and then run it, you can kind of check whether you've got the right step-by-step evaluation because you should see the same value repeated each associated with this video. Just as an aside, so you understand how powerful functions are. One of the most important theoretical results in computer science says that if you have a language that just has functions, no strings, no numbers, just functions, you can actually write any program that can be written in any language. Now, you know that's a theoretical result that makes academics happy. A language like that would be pretty cumbersome to program in, so you would never do it. Back in practical terms now, we want functions, we want strings, we want images, we want numbers, we want all of that. Even so, functions are pretty central to the whole game.
Functions are cool, fun. Okay, I don't really care about all of that. Booleans and if expressions.
Oh, this is the usual mistake where I wanted to use. If you've ever played 20 questions, you know that the answer to true-false questions can really say a lot. And in fact, in computer programs, true-false questions turn out to be fundamental. In this video, what I want to do is talk about a new kind of value called a Boolean. It's going to represent the answer to true-false questions. I'm also going to talk about a number of primitive true-false questions, and a new expression in Racket called if that's going to let us make our programs produce different values depending on the answer to true-false questions. Boolean values are going to represent the answer to true-false questions. So you shouldn't be surprised to find that there's two Boolean values. And in the beginning student language, we write it this way. True is the value that represents the true answer to a true-false question, and false is the value that represents the false answer. And if they're values, if we run them, if we evaluate them, we get the value themselves. Okay, let me comment those out. That's how we're going to represent the answer. What are the questions? Well, let me just set myself up here a bit. I'll give myself two constants, width and height. I'll just make them both be 100.
I think I already have with.
So here's a true-false question. There's a primitive called greater than, and if we say greater than width, height, and evaluate that, run that, we get false because width is 100, height is 100, and 100 isn't greater than 100. On the other hand, here's another primitive, greater than or equal width, height, and if we run that now, we get false for the first one and true for the second one because 100 is greater than or equal to 100. These kinds of primitives that produce a true-false value are often called predicates. So we would say greater than is a predicate, and greater than or equal to is a predicate. And there's lots of others. You can say equals 1, 2, or equals 1, 1. Let me just comment these two out so they don't confuse us. Or greater than 3, 9, and we'll run that. And equals 1, 2 is giving us false, equals 1, 1 is giving us true, and greater than 3, 9 is giving us false. And there's lots of others, and I'll remind you that the 1x lecture video will show you how to discover more of them. Let me just show you a couple more. I'll comment this out now so it doesn't confuse us. There's some that operate on strings. So for example, you can say string equals question mark foo bar, and that's false because those two strings are not equal. What if I want to ask questions about images? So let's see, suppose I want to have two images like this. I1 is a rectangle that's 10 by 20, and it's solid, and it's red. And I2 is a rectangle, and it's 20 by 10, and it's solid, and it's blue. Suppose I want to know which image is thinner. I could say less than image width I1, image width I2, and I can run that. Oh, see, rectangle, this function is not defined.
Oh, okay, cool. So this is so define I1, define a function I1 that basically does 10, 20, solid, red, and then I guess I want like an I2, image 2, which is going to be also a rectangle. It's going to be different shape and color. And then the check, I guess, is this how you write image width of I1? Yeah, this parentheses is quite tricky. Image width of image 2. Oh. Is the width of image 1 less than the width of image 2, right? That's what it's doing. It's true. I guess it's height. No, it's width, height. And then obviously this would be false. Yeah, okay, that's fine.
Oh, this is the usual mistake where I wanted to use image functions and I forgot to put a require. I'll just put the require to http/image. And now if I run this, I'm getting true, meaning that the width of I1, which is 10, is less than the width of I2, which is 12.
Which I think is fine. Okay. What's this? By the way, it's 35% off the gift subs. If anybody said claim your sub, subscribe to myself. Yeah, it's not gonna happen. All right. Yeah, this is the danger of Twitch streaming. Is like it's easy to get distracted. Booleans and stuff is fine. Yeah, I don't want to do any of that. Part 3. Did I do part 2? Huh.
Okay, so that's Boolean values true and false, and a number of predicates that are questions that produce true false answers. Now I want to talk about if expressions, which are going to let us have our program produce different results depending on the answer to true false questions, depending on the result produced by a predicate. If expressions are simple to form, with open paren, if, and then 3 expressions and a closed paren. We call those 3 expressions the question, the true answer, and the false answer. And one key thing is the question expression has to produce a Boolean value. So the question expression usually calls a predicate of some form. Now let's look at an example. Going back to where we were, let me start by just deleting this expression here. And then we'll try to write an if expression that determines what the shape is of I1. So we'll say open paren if, and then let's say less than is the width of I1, less than height of I1. And if that's true, that's the question. If the question is true, then here's the true answer. We're going to say that the image is tall, its width is less than its height. And in the false answer, we'll say that the image is wide. And if I run that now, there's 2 interesting things to see here. One is that the result was tall, because sure enough, I1 is taller than it is wide. And the other interesting thing to see was that right here, this piece of code was highlighted in black. Depending on which version of bracket you're using, it might be highlighted in orange, but it's highlighted. We're going to talk a lot more about that later this week. But if I go ahead now and switch around, maybe I ask the question about I2 instead of I1. Well, I2's width is greater than its height. And in this case, if we evaluate the expression, it produces wide, and the true answer this time is highlighted in black. So you may be able to start to guess what that black highlighting means, but again, we'll talk about that later.
So this is kind of like ternary expressions, I guess. Okay. What is this? Okay. Oh god, this is gonna be fun. All right. Let's run this bad boy. Okay, cool. So if this is true, then this, otherwise that, right? That's fine.
So that's an example of an if expression. What we need to do now is look at the detailed rules for evaluating if expressions. What I'm going to do is first go ahead and put the evaluation rules for if here on the right. And then I'm going to change the example expression a little bit, just to make it a little bit richer so we'll understand the rules a bit better. I'll say that if the width is less than the height will produce the width, that the true answer will be the width, and the false answer will be the height. Now let's try to step through that bit by bit. And I'll also use the Control-E or Command-D command to just make bracket hide the interaction area, so I've got a bit more room to work. So let's see, I've got an if expression.
Oh, it's Command-E, that's cool. Yeah, so okay, to evaluate an if expression, if the question expression is not a value, evaluate it and replace with the value. Yeah, that just kind of makes sense, yeah. If the question is a true, replace the entire expression with true answer. If the question is false, replace the entire if expression with false answer expression. And then the question is a value other than true, false, so produce an error. Yeah, okay, I don't think I need to go through this one, makes sense. Alright, booleans and if expressions, okay. What's
image
this?
1 and image 2. And we know that if we want to find out whether image 1 has a height greater than image 2, we can say this. So that's comparing the height of I1 and the height of I2. And if we run that, we'll get true because 20 is bigger than 10. We can also, if we wanted to, compare the width of I1 and the width of I2 to see, in some sense, this first thing is saying, is I1 taller than I2? And the second one is saying, is I1 skinnier than I2? And that's true. Now, what if we wanted to know whether I1 was both taller and skinnier than I2, if it was both things together? Well, here's a new primitive called and. And is a special kind of expression like if. And the way and works is you can wrap open paren and around any number of other expressions that themselves are going to produce a Boolean value. And what and does is it evaluates the first one, and if that produces true, it keeps going. And if by the time it gets to the end, all of the expressions have produced true, then the whole and produces true. If, on the other hand, and gets to an expression that produces false, then it stops right away and produces false. So and does what's called short-circuiting. It doesn't keep evaluating if it comes to an expression that produces false. It only keeps going as long as the expressions are producing true. There's also a primitive or expression, and there's a primitive function called not.
So I can go and this one, that one, that one, and close off thing. Okay, if both of these predicates are true, if or either one of them are true, and then not true, I believe that's what it says. And or not. So I gave us a true. So let's flip it so we get a false. I mean, it's an. Okay, if either of them are true, so I guess that's all. Is that right? Less than 10, 20. What's I don't actually know which part is height, which part is width, so let's run that. That gives us a false. Is it greater? So that gives us okay, so I expected okay. Yeah, so basically if I do that, we should no? Isn't that what an or is? If either of these are this is true, right? No? That's false. Okay, never mind. I'm gonna flip it. Yeah, okay. That should give me a true. Yeah, okay. Alright. I know you mentioned not, but I don't know how to use not yet. Oh, we'll move on using a stepper. It'll be interesting.
In this short video, I want to show you how to use the stepper, which is functionality built into Dr. Racket that can help you understand the step-by-step evaluation of complex expressions. I have the stepper starter.racket file open here. And if we look at this file, there's one expression here at the top, a simple expression, and then a function definition and a call to that function. If we look at this expression, let's see, plus times 3, 2, that's 6, plus 1, that's going to be 7. That's easy enough to see. And here we're calling maxdim with a rectangle, and there's an if, and it may be a little bit harder to quickly see what the result is here. Let's run it. Let's see, that produced 7, and the call to the function produced 20. And you could try to work through this and see why it's 20, and maybe you can see that quickly, or maybe you can't. What the stepper's for is to help you understand how the evaluation of expression produced a certain value, in cases where it's too complicated to just see. So let's try running the stepper. I'll say step here, and I'll make this window a little bit bigger. And what the stepper does is it goes through the file and it follows the beginning student language evaluation rules. So the require doesn't produce a value, the require is just a declaration. So it has to be evaluated. Open paren time, because the first operand is not yet a value. It wants to evaluate the call to image width. It can't do that because the first operand, that's what's happening here. Here's the false answer expression, and the entire if gets replaced with. If you want to, I'd encourage you to learn how to use the stepper. In this video, I'm going to talk about how you can discover more primitives than the ones I cover in the videos. In the beginning student language, there's far too many primitives for you to learn them all, and far, far too many for us to cover them in the videos. So you need to be able to discover primitives on your own. And in other programming languages, there'll be even more primitives that you need to be able to discover on your own. So what I want to talk about is two general techniques you can use for discovering primitives. Now the first one, you're going to laugh at this, the first one is actually to make a lucky guess. You may think that's crazy, but it turns out that what happens after you've been programming a language for a while is you start to get a pretty good sense of what the naming conventions are. And it turns out you do manage to guess the name of a new primitive more often than you might think. Let me show you how that works. Imagine now we go back to where we were in the strings and images video. I know there's circle, rectangle, and text. I might say, well, gee, I wonder if there's something called triangle, and I could just try it. And I guess triangle must have some kind of size. I'll just put in a number, and it probably has something like a fill and a color, so let's just say solid, and we'll say purple. Again, I'm just trying this to see if it works. And sure enough, it does seem to work. At this point, I might wonder, well, what exactly is that number 40? And then I could go up here to triangle, click on it, and on my Mac, I'm going to control click, on Windows, you would right click, and say search in help desk for triangle. And this is going to bring up the Dr. Racket documentation for triangle. And I want the one from 2HTTP image, so I'm always going to select the one from 2HTTP image. And it says that the first number is the side length. So I know that 40 is this side length right along there. That's the 40. So you can guess, and often you can guess right. That's the first technique for discovering new primitives, is to make a good guess. Another good trick for discovering the name of new primitives is called search and scroll, or look up and scroll. Imagine that what I'm doing is I'm writing some expressions that in my racket, like this one, divide 3 by 4. Now if I run that, of course, I get 0.75. But maybe what I really like to do is round that to the nearest whole number, like 1 in this case. There must be a function in racket to help me do that. So here's how the trick works. I find a place in the code where there's a related function, in this case divide. Divide's kind of like round, it operates on numbers. And I control click on top of divide, or on Windows, I right click. And then I pick the menu item search in help desk for slash. Now the thing is, racket supports a lot of different languages. Okay? I want to choose the documentation for slash from HTTP beginner. I want to choose this line of it here. And so I'm going to click on that slash right there, and that'll take me to the documentation for this version of divide. And here I am, and goodness gracious, there's a whole bunch of functions here that look like they operate on numbers: divide, less than, greater than. And what I'm going to do is I'm going to scroll through these, and I'm going to try not to pay too much attention to the list, because there's a lot of these functions. So I'm just kind of scrolling my way through this list. I need to not get lost in all these functions, or else my head is going to explode. But I'm scrolling. And eventually, after just a whole lot of scrolling, in this case, there are lots of functions that operate on numbers, I will come to a function that is the one I need in this case, and here it is, round. And round does what I want to do. It rounds a real number to an integer. So now I've got what I need. I go back to racket. I put round around the previous expression, ha ha ha. I run that, and I get 1, which is what I was looking for. So the trick here is to look up the documentation for a related function, and then scroll around looking for the thing you want, without getting lost in all the very, very many functions that racket provides.
Okay, that's fine. It says command click. Is that what I did? Search for help desk. Oh, there we go. Yeah, it's good to have documentation right here. Can I just have it as a link? So I can copy for later on? Yeah, okay, cool. Oh no. And I can just right click and go, but I like to have a copy pastable right at the top. Beginning student language documentation, I guess. Okay, I think we're making good progress right here. Let's go back into the course. What is the name of the primitive you'd use to produce this image? Ooh, I mean, that looks like a star. I mean, radial star even? I don't know, let's just try. What? Guess not. Function call. Do I need to go? Oh, I mean, yeah, it's gonna need some stuff on that. Okay. Star 10 5 red. Does that do anything? Nothing. 10 red color. Expects 3 arguments. Okay. Yeah, this is a good one. So if I know, this is quite annoying. Star. Yeah, I mean, there's all kinds of stuff. Side length, side count, step count, mode, color. Side polygon. Side solid. That's what I need. Okay, it's a very small star. I guess that's a radial star. Expects 5. Yeah, okay. Side length, side count. No. Point count. Initial radius, outer mode, pen or color. A lot of stuff. Okay, so point count. So I only want it to be like 4 points, I guess. Inner radius, that can be 8, I guess. I don't really know what that means. Outer radius, okay, let's just copy that. 64, solid, red. Yeah, okay. I mean, kind of obvious, right? Not obvious, but like kind of intuitive. Yeah, okay, cool. That's fine. We can play with this later on, sure. Yeah.
So that's 2 ways you can discover new primitives. You can either guess, and you'll be surprised how often you get lucky, or you can look up the documentation for an existing primitive and scroll around to find related primitives. As you program more and more, you'll get to know more and more primitives, and you'll be able to guess lucky more often. You're also going to see that programming environments, that's editors like Dr. Racket, have tools that help you guess more quickly. And we'll look at some of those in later weeks of the course.
Okay, so we got somebody got some bot in my. How do I ban this bot? How do I ban this Twitch chat? I guess. Stream. Stream manager. Is this where I would go to? It's very annoying when this happens. Where did it go? Safari. Ah, I moved it to a different. Yeah, that's not what I want. That is not what I want. Okay. How do how do I delete this message, guys? Click to reply. No, I want to delete it. Pin. No, I don't want to pin. I want to delete this message. There we go. Yeah, I don't want to show anything like that. Okay. Alright, let's move on. What else we got? Primitives, discussion, don't need that. Problems. Yeah, we should probably do problems. I want to do problems later on. I want to go through just the content here, get the things, and then just wrap up. Feedback. What is this?
Hi everybody, I just want to check in and give you some thoughts about what's going on in the course this week. This is always a really fun time in a MOOC when everybody gets on for the first time and there's all the introductions and you see where everybody's from and what kinds of things they're hoping to get out of the course. And I've really been enjoying reading those introductions and all the other forums. Let me just talk about a couple things on the forums. So one of the threads had to do with which of the 3 ways of computing average was in some sense the most clear. And most people thought it was number 1. Some people pointed out that in some sense it didn't matter. The people who pointed out that in some sense it doesn't matter are technically right. Either way, or any of the ways, you get the same number when it's evaluated. But we kind of like the first one best. And in fact, one of the notes that was posted from Craig McDonald, and in fact, Craig points out that the first choice is the one that most closely matches one of the themes for the course, which is learning how to write code that looks like the design. If you didn't pick that one, if you picked the third one, that's fine too, or even the second one. Stick with us a bit, and we hope to convince you by the end of the class that really you'd prefer to write the first one too. And you can come back and debate that with us later on in the course. So another thread that was fun was the thread having to do with all the images. And here I'm showing you some of the images that people uploaded. We weren't able to put all of them in here, but there's a lot of great ones. Faces seem to be particularly popular every time. And if you haven't had a chance to create your own image yet, maybe you can use this set of examples as inspiration over the weekend for you to do one of your own. Finally, just a note about the wrap-up. We enjoyed reading the comments in the wrap-up, and especially the suggestions for how we can improve things. A couple people asked for more problems to do, and I just want to point out that if you go to the top of the screen, there's a tab that says Problem Bank that has a lot. Those add up to a significant fraction of the course.
How to design? Yeah, I think this would be good. How to design functions. Let's see. So we get. All right. How to design functions. It should be new material even for people who programmed before. Yeah, probably. So you need to use some kind of recipe to operate on primitive data. Be able to read a complete function design and identify its elements. Be able to evaluate the different elements for clarity, simplicity, and consistency with each other. Be able to evaluate the entire design for how it solves the given problem. Kind of want to try like see if we can get some people in here for yeah, let's see if we can get some. Hey guys, hey everyone. I don't know if it's. There's the rules here. So one link. But like streaming. Judge if anybody. Cool. Okay, I'm missing that message. I don't know. Maybe people want to hop on. We'll see. How to design functions. So. At first, it may seem like an overkill. It may seem overwhelming. You may suspect that these functions could be written more quickly without the recipe. You're right. Design methods often make simple problems hard to solve. Right now we're using simple problem to learn a design method. This will pay back later when you make really hard problems easier to solve. Planning your time. This will take approximately 47 hours. Yeah, To help you master design my first. Yeah, okay. I don't think we need that. Alright, cool. So I kind of have an idea of what this is because I went through it before. But hold on, recipe.
In this video, I want to introduce one of the most important elements of the course, the How to Design Functions recipe, or we call it the HTDF recipe for short. The HTDF recipe systematizes the design of a function. What I mean by that is it tells us what to do first and second and third all the way through the design of a function. So it helps us know what to do, and it also helps us be sure that we end up with a high-quality function that really does what we need it to do and that's been well tested. Now, there's a funny thing about design recipes, or design methods as they're sometimes called. It particularly affects when you learn them. What a design recipe does is it makes hard problems easier. It lets us take a big hard problem and break it down and work through it in a systematic fashion. The price we pay for that is that it actually makes easy problems more cumbersome. That's right, the HTDF recipe is going to make hard functions easier to design and easy functions a little harder to design. In fact, once you get good at designing functions, you won't use the HTDF recipe for really simple functions. But for now, we want you to use the HTDF recipe even for simple functions. That's because the way this is going to work is that you're going to use simple functions to learn the recipe, and then you're going to use the recipe to do the hard functions. So what I need to ask for now is two kinds of patience. If you've never programmed before, it's going to seem like there's a lot going on when we introduce this recipe. So I'm going to need to ask that you be patient and go through it with me at the pace we're going through, and I promise you it will become familiar. If you have programmed before, this is going to seem like overkill. We're going to start with a very simple function, and by using the recipe, it's going to take us quite a long time to do it. I need to ask you to be patient too. I promise you, within a few weeks, by using the recipe, we're going to be designing much harder functions than we could design otherwise. Here's how we're going to go through this material. There's going to be this video and the next one. In the first video, I'm going to go through the design of a function step by step, and I'm going to tell you what I'm doing at each step, but I'm going to describe it as if you already knew the terminology of the design recipe. I know that sounds silly because you don't, but we've learned from teaching this to many, many students at UBC that the right thing to do first is to kind of go through it at almost normal speed. Then in the next video was going to kind of be a slow motion version of this video. In that next video, as we go through it piece by piece, I'll elaborate on each piece we're doing and why we're doing it and how it works. So what we're going to ask you to do is watch this video once at speed, then watch the next video with Dr. Rackett open, following along, and then it'll probably help you to watch this video again at speed. Everything we do, the entire design recipe, you can find on the course webpage under the design recipes link. That example that's used on the website is the one we're going to do here, so you'll be able to follow along. Again, be patient with material and be patient with yourself. There's a lot going on in the HTDF recipe. You're not going to pick it up the first time through. You're not going to pick it all up the second time through. But you'll be going through the recipe hundreds of times through the course. And I promise you, within a couple weeks, it's going to seem quite familiar, and you'll just be learning more nuances about it as we go forward. Okay, now what I've done here is I downloaded the doublestarter.racket file from the HTDF module webpage, and I've opened the file up in Dr. Racket, and it's giving me a problem that we need to solve, a design problem. And what it wants us to do is design a function that consumes a number and produces twice that number. We're supposed to call the function double, and we're supposed to follow the HTDF recipe. Now, whenever I follow the
Okay, I know there's a way to insert comment box. Yeah, that's what it was. I should probably just copy the file, but I don't know. Design a function that consumes a number and produces twice the number. Call your function double. Follow the HTDF recipe and show the stub. Can't remember the stub and template. Alright, this is a little. Hopefully, okay, that should be enough to see.
The HTDF recipe, I like to have a copy of the recipe right in front of me. And so what I've done here is I went to the Design Recipes tab on the course website, and then I followed the link to the How to Design Functions page, and then at the top here is a quick summary of that recipe, and I copied that in my video editor and put it right here so we can work. So step one is the signature, purpose, and stub. So this function is going to consume a number and produce a number, and that's the signature for it. The purpose of this function is to produce 2 times the given number. And the stub is something, remember, in the next video I'll go through more detail about this, but the stub is going to look like this. It's define the name of the function, a single parameter which I'll call n, and the stub is going to produce 0, and as I said, we'll talk more about what's going on there in the next video. So there's step 1, signature, purpose, and stub. Now I'm going to do the examples. Now what I'm going to write for the examples is I'm going to write check, expect, and then a call to the function double of,
kind of like
let's say 3.
test.
And then I'm
It's
going to
almost a
write 6,
test of
if
an
I call double with 3, I expect to get the result 6. Now if I call double with, for example, 4.2,
TD.
I expect to get 8.4. So that's my examples. I'm going to run my examples, and they're going to fail. Both tests are going to fail. Again, we'll talk more about this next time. But the fact that they even ran told me something important, which is that the examples were well formed. Now I go on to the template step, and the template for this function is going to be just define double of n, and then ... n. And the way I'm going to read that is it's going to say, you know, when I get around to coding the body of the function, n is what I have to work with. The actual parameter is what I have to work with. So there's the template. Now I have to go on to the step of coding the body. To code the body, what I do is I make myself a copy of the template. I take the old template and comment it out. And now I have to figure out, well, what is in the body of this function? What's going to make the body of this function work? And now I'm going to look at the examples, I'm going to look at the signature, I'm going to look at everything I've written before, and what I'm going to do here is actually I'm going to elaborate the second example just to make this more clear to myself. I'm going to say, look, the reason it was 8.4 is that it was really 2 times 4.2. And now I have my aha moment. I understand what the function's supposed to do. It's times 2 of n. I run it, both tests pass, fantastic, I have the sense of my function's working. So that's a first pass through the HTDF design recipe. Again, I certainly don't expect you to have fully absorbed the HTDF recipe from that quick pass through it. What I want you to do now is go to the next video, which is going to be the slow motion version of this video, in which I'll talk about the different parts of the recipe in more detail.
Okay. I kind of want to follow along this one. I'll get the gist there.
We'll see examples later about what to do when the tests don't pass. In the last video, you saw me use the HTDF design recipe to design a very simple function. But I went through it very quickly, too quickly for you to absorb the different elements of the recipe. What I'm going to go through in this video is the same design much more slowly, and talk more carefully about what I'm doing at each step. What I recommend you do is have your computer open up Dr. Racket, and follow along with the design recipe as I'm going through. At each step, you could stop the video and catch up in your Dr. Racket. And I also recommend that you open up a web browser to the HTDF design recipe page from the course website so that you can follow along with that as well. Then you'll be able to see what I'm doing and practice it as it's going through. Just like before, I've taken the double starter.racket file from the HTDF module webpage. I've opened it up, and here's the problem. We're supposed to design a function that consumes a number and produces twice that number. And the function should be called double. Again, it's a very, very simple function. Remember, we're using simple functions to learn the recipe, and then the recipe will let us do harder functions. And also, just like in the full speed version of the video, I've taken a copy of the How to Design Functions recipe, which I got from the design recipes page, and I'm setting it here on the right-hand side so we can refer to it as we go. The first step of the recipe is to write the signature. The job of the signature is to tell me what type of data a function consumes and what type of data it produces. In this case, the function consumes a number and produces a number. So I write the signature with 2 semicolons, a space, capitalized number, type names are always capitalized, and then I make a little arrow, and again, capitalized number because this function produces a number. If the function consumes multiple arguments, then I have multiple type names before the arrow. In this case, it just consumes 1 argument, and I read this signature as saying the function consumes a number and produces a number. Now I need to write the purpose. The job of the purpose is to give me a succinct description of what the function produces given what it consumes. So in this case, a good purpose is to say that the function produces 2 times the given number. Now I know exactly what it's producing in terms of what it consumed. The purpose needs to say more than the signature. So a purpose, for example, that just says consumes a number and produces a number isn't telling me any more than the signature, and that wouldn't be a good purpose. We also want the purpose to be short. Sometimes it's hard to write it short, less than 1 line, but it's good to do so because it starts to help you understand the function. And the stub is like a piece of scaffolding that we're going to put in place for a short period of time. It's going to help us with some other parts of our work, and then we'll end up commenting it out, or later in the course we'll just actually delete it. So it only lasts a short while, but it will do an important piece of work. What the stub has to be is a function definition that has the correct function name, in this case double, has the correct number of parameters, in this case 1, I'll just call it n, and it produces a dummy result of the correct type. Since this function produces a number, I'll make the stub produce 0, because 0 is certainly a number. So now I'm going to write the examples and tests. We call them examples and tests because they're going to serve both roles. What I mean by examples is that oftentimes it's easier to design a general function if we start with some very specific examples of what it's going to do. So in this case, for example, I might write check expect that if I call double with an argument of 3, then what I expect to get back is 6. And I'll also write check expect that if I call double with an argument of 4.2, I'll expect to get back 8.4. The reason I'm calling double with these 2 arguments, the reason I have 2 examples, is I've said here in the signature that the function consumes number. And by number, I mean real numbers, integers, natural, all kinds of numbers. And so I'm going to put 2 examples here just to really illustrate that I don't just mean integers. The first example might lead you to think I just mean integers. We're going to talk a lot in the course about reasons to have multiple examples and how many examples are enough for a given function. But here's 2 examples for this function. Because I wrapped them in check expect, they're also going to be able to serve as tests. And we'll see shortly how they're going to help us code the final body of the function. But first what we're going to do is make sure that the examples, the check expects, are well formed. And here's where the stub's going to help us. What I'm going to do now is I'm going to go ahead and run this program. And when Dr. Racket has a program that has check expects in it, what it does is it runs the check expects, and it checks to see, for each check expect, it will call double with 3, and it checks to see whether the result is 6. And then it will call double with 4.2, and checks to see whether the result is 8.4. And if the result isn't what it's supposed to be, then Dr. Racket reports that the test failed. Now in this case, both tests failed, and I'm very happy. The reason I'm very happy is both tests actually ran. Here's what the stub is doing for us. It's letting us make sure that the tests actually run. They're going to fail because the stub always produces 0, and that's not the right answer for these. When we start to get big, the easier it is to point. Now, the helps us write the perfect argument, so this function has 1 parameter. It's a number, that's why I called it n. Write the check expects number to the argument. For this week, the template is going to be quite simple. The template is a function with the right
Interesting that he moved it around. Did he move it around in the video?
I'm going to go ahead and run this program. And when Dr. Racket has a program that has check expects in it, what it does is it runs the check expects, and it checks to see, for each check expect, it will call double with 3, and it checks to see whether the result is 6. And then it will call double with 4.2, and checks to see whether the result is 8.4. And if the result isn't what it's supposed to be, then Dr. Racket reports that the test failed.
So of course it's going to fail for us right now.
And I'm very happy. The reason I'm very happy is both tests actually ran. Here's what the stub is doing for us. It's letting us make sure that the tests actually run. They're going to fail because the stub always produces 0, and that's not the right answer for these cases. but we're going to know that they ran. And you'll see later as programs start to get big that making sure all your tests are well formed before you get farther along in the process is a good thing to do, because the sooner you find a mistake, the easier it is to fix. So here we go. Both of these tests ran and they failed, and I'm really happy. I want to take a minute here to make an important general point about the recipe, and that is that every step of the recipe is intended to help with all the steps after it. For example, the signature helps us write the purpose, because the signature tells us that the function consumes a number and produces a number. Similarly, the signature helps us write the stub, because the signature says the function consumes a single argument, so this function has one parameter. It's a number, that's why I called it n. It also tells us that the function produces a number, that's why I chose 0 as the dummy value for the stub to produce. The signature also helps us write the check expects. It tells us that this function, when I sit there and write check expects double, and then I ask myself what to put, well, the signature tells me put a number. And then when I try to write the expected value, the signature says that it's a number, and the purpose tells me exactly how that number relates to the argument in the example call. The key thing is when you're trying to figure out what to write at one step of the recipe, look at what you wrote at the previous steps of the recipe. That's how the recipe is helping you, is it's letting you slowly build up the knowledge you need to design the final function. The next step of the recipe is the template, or sometimes called the inventory. Starting next week, we're going to get richer and richer templates. But for this week, the template is going to be quite simple. The template is a function with the right function name and the right parameter. And for this week, the body of the template is just going to be open paren ... n. And the way we're going to read that is we're going to read that as saying, hey, the outline of this function is that it's going to do something. That's what the dots mean, is do something. It's going to do something with the parameter n. That's the role of the template, is to give us kind of the outline of the function. What I'm going to do here is label the template, and now I'm going to make a copy of it. I'll put the copy here, I'll remove the label from the copy, and I'll comment out the original template. What you're going to do later in the course is you're not actually going to keep a copy of the template, but we found for the first few weeks of the course that it helps to keep a copy of the stub and template around, and that's why that's what I'm doing here. There's the template. It's the outline of the final function definition. Now I'm going to code the function body. In this step, I'm going to use everything I've written before to help me know how to finish the function body. One thing that's useful to do sometimes is elaborate the examples. So in this example, I know that double of 4.2 is 8.4, but what I'm going to do now is make it more clear to me why that's true. The reason that's true is that it's times 2 of 4.2. And now all at once I know exactly how to finish this function body. It's just times 2 of n, whatever n.
Right. Okay.
Is.
Okay. Everything passed? Cool. Alright. So this is gonna get annoying having everything in one place, but we're just gonna have one big file, man. It's okay, it's fine. Okay, that's cool.
The last step is to run the tests. So I run the tests here, and I get both tests passed, which makes me pretty happy. We'll see examples later about what to do when the tests don't pass. Now you've seen the HTTF design recipe used twice to design the same simple function. In the last video, I went through it quite quickly, and in this video, I went through it in slow motion where I talked in detail about each step.
Please spend 30 seconds just thinking about what the half TW function does before going to the next step. Okay, so we have two constants, define half TW, takes x, it adds x with something, it's the difference between x and the width divided by 2. Yeah, so okay, so it's x. Yeah, x plus half of the width. Width minus x. So it's x plus x minus 100 divided by 2. Yeah, I think that's it, right? Oh, it'll be easy to write it like this. Okay, number. So it takes a number, gives a number. Given a y coordinate, produce a y coordinate halfway between it and height. Halfway. Oh, okay. Yeah, it's a very mathematical way of thinking here. Like how the yeah, this isn't it's crazy. Okay. I'm just gonna go 1 here because height and width have already been used above. Make sure that still works. So for test so fast. Check expect half. It's a little cumbersome. I don't know if it's complex, but I think it's helpful, I guess, to understand this. Hang on, do I understand this? So we have a number, and then the way you do it is, so if I have 20, width didn't come into this. Width doesn't come into yeah, this is just an example. Half th. So given a y coordinate, find the y coordinate just like somewhere there. Halfway would be x minus, well no, y minus x. That's basically what it's doing. So we have height, that's 100. We have y. Yeah, okay, yeah. Purpose. Don't need that, stop. Yeah, like just doing this is gonna be time consuming, but I really wish these things worked. It doesn't work. Can I open? Okay, so knowing how to do this. So I think is it in problem downloads? No. Code. Can I not? Code. City starters. Week 1. 1A, 1B. Where are we? Full speed. Yeah. Okay. Yeah. Right. That's what we want. We want the starter. Okay. That is actually quite helpful. I think we're just gonna go through that. Design a function called yo that consumes strings and adds a bang, produces string. Okay, so this is gonna be okay, what the hell? So I'll design function, signature, I think we need all of that. Okay, so signature is gonna be, it takes a string, string back, so basically adds a exclamation at the end of the string, given string really, and then check expect example to be check expect the function yell like this one here. I think that's how you write the check expect. Is that right? Yeah, I don't want that one. Yeah, okay. I think that's templates. What was the template like? Just define yo. It takes a string. How do you do how do you do function definitions? Like, oh, okay, yeah, okay, alright. So I forget how. So yeah, it takes a string and it'll basically string append is what we need. mean, that's kind of the answer here. So I'm not sure what the template would look like for this, but alright, so I run that, should pass. Save all files. Test passed, yeah, exactly.
In this video, I'm going to work through a relatively straightforward how to design functions problem. So this video would be a really good chance for you to practice what you saw in the HTDF full speed and slow motion videos. Just get the starter file and start working the problem yourself. And every now and then run the video to kind of catch up to where you are in the problem so that you can see that you're doing it kind of the way that I'm doing it in the video myself. Okay, this first function is going to be simple, a lot like double. You need to design a function called yell that consumes strings like hello and produces strings like hello bang, where the exclamation mark has been added to the end. Let's see, the signature of this function is it consumes string and it produces string. And what it's supposed to do is produce string with bang added to end of supply.
I think this is what the template looks like.
That's a little cumbersome. Unpurpose statements are often cumbersome the first time you write it. Let's see if we can do better than that. What if we just say add bang to the end of s, where s is the name of the parameter in the stub. So that's simple. Add bang to the end of s. Okay, let's write a check expect yell with hello. It better produce hello bang like that. And check expect yell with bye. It better produce bye bang like that. Now we run the tests, run the check expects, and both are failing, but the key thing is both are running, so that tells me that they're well formed.
I don't see the point of adding two different tests that's identical there. Doesn't make any sense.
We'll comment out this stub and we'll label it as being the stub. And let's see, the template for this function is define yell of s.
Oh, okay.
S.
So the stub is really the function body, or like how you would call the function. Is that what a stub is? And I also like to just use S, but I'll probably use interesting, but okay. I guess so. Stub is not a stub is how you would call the function, and then a template is how you would write the function, I guess, right? String and then there's gonna be some operations on string, right? Yeah, I think this is how you do the template. I think I should do a pass. Okay, let's continue.
What we're going to do is select the template, make a copy of it, paste copy here, comment out the template, and label it as being the template. Later in the course, you won't have to leave the template behind, but for now, we find that it's helpful. There's the template, and now I need to edit it. And oh yeah, what this function does is it produces a new string by adding bang to the end of s. So that's just going to be string append s and bang like that. Now we'll run it again, and both tests pass. So there we go. That's the design of the yell function following the HTDF recipe.
Yeah, okay, that's pretty straightforward. I'll probably, yeah, okay, we'll keep using that. Okay, so this is gonna be my notes, and we'll keep opening the other one. Okay, cool. I think we have a game plan. All right, one's for free. I kind of want to go through. Maybe. Can I open? It's week 1A. Was it 1B? Yeah. Slow motion. Yell. Starter. Was this my? No. Man. Nope. Okay, this is what I want. Copy. And yeah, I'm just gonna paste that in there. Just get all 5 tests pass. Okay, that's fine. Rather keep it in one place. Okay, alright. What's this? Area.
How to design functions problem. In this problem, we're going to see a few extra wrinkles, including an example of how not to write a good purpose, some problems that can come up with tests, and some issues having to do with copying part of what's in the template. Okay, so here's the example. I'm going to design a function called area. It consumes the length of one side of the square and produces the area of the square. Let's see, so the length is going to be a number,
Okay, so before I watch the video, I kind of want to see, was it Command C? I forgot how to do that. Okay. Design a function called area that consumes the length of one side of a square and produces the area of the square. Area of the square is just like times itself, right? By this. Okay, so basically it's gonna take a number and it will produce a number. What were the steps again? Yeah, okay. Purpose is calculates the area of the square given one side. I guess that makes sense to me. Purpose, a stub would be, I think define area. Takes number. Right, that's how you define yep. We need some check expects, I think. Is examples wrap. Okay, check expect area of 2 will give us 4. I mean, what else is there? I think 1 is enough. What else can I check, right? Like, it's just what it is. I mean, I guess you could have a non-whole number. Like 2.4, I don't know what 2.4 is. 5.76. Is that right? 2 times 2, 2.4 times 4. I think so. Okay, so we have that. Template's gonna be area takes n. Do something to n. I mean, so these templates are kind of annoying to write. Okay, but okay, define an area side, and then it's just gonna be right. And let's see if that passes. Oh, 7 passed. Yeah, okay. And I'll assume that's basically it.
And the area of a square is also going to be a number, so the signature is number to number. And the purpose is given length of one side of the square, produce the area of the square. Let me just make a note here about what's not a good purpose. This is not a good purpose. Given number, produce number. That just repeats the signature. That's not telling me something we don't already know. The purpose needs to tell me something more specific than the signature about exactly what we do with the given number, exactly what the number we produce means. So given the length of one side of the square, it says this is the length of one side of the square. Produce the area of the square. This number is going to be the area of the square. So that's what we want the purpose statement to do, is be quite specific about what's going on. So now let's see, the stub is define area. This is a 1 argument function, and maybe the length of the side will be s. We can use any name we want, but s seems good. And let's see, this is producing a number, so a good dummy value produces 0. And let's do some check expect. Let's see, check expect area of 3. Well, if one side of the square is 3, then the area is 9. And we'll do another one, check expect area of, let's say, 3.2. And let's see, the area of that square is times 3.2. 3.2, I won't try to do that in my head. Now we run the check expects, and both ran. They failed, but they both ran. So that means they're well formed. We can continue. Now let's see, we've got the stub. Let's comment out the stub and label it. And we'll write the template area. The parameter s is a number. The template is ... s. And it's going to be good to have a copy of that template, so I'll make a copy of it right there. We'll comment out the original template and label it as the original. And now let's see. This is a function that consumes the side, and it just multiplies the side by itself, so this becomes times ss. Let's run that. Oh, we got a failing test here. Let's see what's happening. This says that the actual value 9 differs from 3, the expected value, and I can click to see which test it is. Let's see, it said it produced 9, and oh, here's the thing that happens. This test is actually wrong. That's not supposed to be 3. That's supposed to be 9. Now if we run it, both tests pass. So So there's two interesting things in this example. One is to note that you need to be careful if you get a failing test to make sure the test is right. If your test is wrong and you make the function conform to it, then the function will be wrong. And that happens. Sometimes you write a test and you're just going a bit too quickly and you put the wrong expected value. So whenever you have a failing test, first look at the test to see if the test is right. The second interesting thing that's happening in this example is to see that sometimes you have to copy part of the template. Remember, the template for this function was ... s. And in the final function, we ended up with s times s. And so we copied a piece of the template, and that's okay. The template is really trying to tell you, hey, here's the stuff you have to work with. You can use it in any way you want. It's just telling you this is the parts list. You can use s twice. So there you go. That's our second function. I'll save it, run it one more time.
Okay, so the changes that I'm making here are basically stubs should have like the output. So I had nothing here before, so that was something I missed. Another thing I'm noticing is so I had it computed with 5.76. Really, you should have it. You should have it says only one number. Like this should have been 2 times 2 as well. So then you know what the answer is. Now I don't know how this will sort of play out when you have more complex functions. I don't know, like the level of detail you have to go through to compute it. And the test kind of maybe it makes sense. I'm not sure, but not quite sure. Yeah, okay, that's fine. Okay, that was good. I kind of want to use this as like I mean, okay. All right, we move on. Questions. Want to do that? Want to do that right now? Image area.
Use a floating point number like 3.2. It's always going to produce a natural. Here's another how to design functions problem. And again, it elaborates on the problem we saw before. What I'm going to do in this problem is when I start out, I'm not going to choose the best signature, and then we'll fix it later. And the reason I'm doing that is I want to illustrate to you that the how to design functions recipe is not intended to be what's called a waterfall process. It's not intended to be something that you do the first step, and then the second step, and then the third step, and absolutely get each step right. It happens pretty often that you go through the recipe, and you get to kind of the third or fourth step, and maybe you realize, oh, the signature is not exactly right, and you go back and fix it. And sometimes what even happens is you skip a first step to go to a later step just to get started. A common example is you're not quite sure about the signature, so you go write some examples, and then you come back and do the signature. Now, what I don't want to do is give you carte blanche to jump immediately to the function definition and do that. That's not going to be what we're going to call systematic design. But I also don't want you to feel like, gee, I just don't know what the signature is, but I'm not allowed to do anything else until I write it. There is some flexibility in following the steps of the process. It's a structured process, but it's not a locked-in waterfall.
Okay, so I kind of want to do this before again I look at his answers. Okay, so I design a function called image area that consumes an image and produces the area of it. Okay, so it takes an image and it gives like a number basically. So we can write that in. So it takes an image and produces a number. And this is basically the signature. Is that right? Yeah, signature. For the area, it is sufficient to just multiply, I guess it's meant to be. Multiply the image's width by its height. Okay. The area is a multiple of images width times height. Okay, right. So the stub define these things always trap the image area is the function name. And I'm just gonna take an image that will produce a number, right? Stop. Move that there. This black and yellow is actually quite pleasing to look at. So this one's gonna be a purpose. I should probably have double quotes too, like signature purpose, stub, and then probably some check, expect, like test basically. So check, expect, image, area, cat, because I have a so it's gonna be a multiple of. Okay, this is where having the things here helps. I might just copy that cat. And I'm gonna go oh cat, just so like. Cause this is just so I don't break the thing, because I want to copy this and make that the cat, that the image here at some point. Define cat. Okay. And probably want to do that there. Okay, cool. So we're gonna do merge with cat, for example. And then the height, I guess, is the I don't recall if that's how you do the thing. Images, where are you? Image with image. Yeah, okay. I think it's fine. Should probably do it like that. I think makes sense. So this will be like tests, basically. Test slash expectations, like that. Okay, and then these parentheses are gonna kill me. Is that like? Yeah, we need one more. Man, these okay. I should do image like that. Because the cat would probably okay, whatever. Okay. What was the other ones? So we've got signature, examples, template, and inventory. Template. So template would be I think like this, like image area that takes an image. Define an image area that takes an image. I mean, this is kind of the solution. Like I don't know. It's yeah, this is where I'm confused on what does the test look like. I guess I'd use like 4 or 5 or something. I'm not sure. Because this is basically the solution right here, but with it takes an image, and then it does and it basically multiplies these two. Is that how you write? I don't know. How do you write? I mean, that should work. Well, whoa. That's a previous example. Okay, that's fine. Yeah, okay. Image variable is not defined. Check expect. I guess this is where I wanted to use cat. Makes sense. Cat is used here before its definition. Where? That's gonna be. Yeah, this is what I wanted to avoid earlier. Because I have in a single file. Okay, all test pass. Alright, so this works. Now this is what I'm not sure about. Maybe this should be like just put in numbers that are 2, 4 or whatever. Just do that. I mean, I didn't even write the template, I just went straight into define, image, area, image, and that will kind of give like some kind of. This is a stub. Oh, no, I have a stub here already. That will do something with the image. I think that's the template, right? I believe. Is this, yeah, this would be how I would do it, but I'm not sure. Again, I'm not sure about this test here. So let's see what he says.
Waterfall process. So here we go. Let's do this example. In this problem, we're going to design a function called image area that consumes an image and produces the area of that image. And it says for area, we just need to multiply the image's width by its height. So let's see, this function consumes an image, and it produces the area of the image. Now, you might think this should be number, and that's actually going to turn out not to be right. And I'm going to go ahead and pretend that I put number for now. Because one of the things I want to show is that sometimes you realize partway through the process that a piece of what you did before isn't right. I'm just going to put number for now. And I'm going to say produce image's width times height, or area. Let's see, the stub is going to be define image area. I like to abbreviate image to img, and a good dummy value is 0.
Yeah, I guess that could be simpler, like area of the image, just like width times. I like that produces makes sense, so that's the purpose, that's what it gives. Produces the area of the image, which is that, right? I think that's what we want. Okay, that's fine.
0 because it's a number. And now let's do some examples. Check, expect, image area. Let's say I have a rectangle that's 2 wide and 3 high, and then it's just red. Well, what's the area of that? Well, the area of that is times 2, 3. All right, let's run that test to see if it's well formed.
Yeah, we can get rid of the cat. I mean, cat's cool, but like, that makes it simple because yeah, that's what I mean. Like, yeah. Rectangle, 2, 3, solid, red. Right, so if I have a rectangle, rect, define image, img, Yeah, this is much cleaner so for you of doing it. And I should like, I think we'll use the cat later on, so just leave it like that for now.
Uh-oh, rectangle is not defined. Oh, that's because whenever we use image functions, we need to tell Dr. Racket that we want to use the image function, and I forgot to do that. So we're going to say require to HTTP image. This is a very common mistake, and I made it here on purpose so that you would see it happen. You just forget to do the require. Now that we've done the require, the test is actually running and failing, but it's running, so we're doing really well. Let's keep going here, define image area. So that's the stub, we'll label it as that. We'll do the template, which will be .img.
So I also like how he just defined. I mean, this image, because he just passed it in, I guess.
Now we'll make a copy
Curious.
of the template. We'll comment out the original template and label it. And now what's this going to be? It's got to be the image's width. We're going to use image twice because we need width and its height. So we're going to use image twice. We're going to say image width of the image and image height of the image. And we're going to multiply those two together. Now let's run that. And the test passed. But now we might realize this interesting thing, which is that images are always sized in pixels. And pixels are always a natural number, 0, 1, 2, 3, 4, 5, something like that. You can have 3.2 pixels. That's not how pixels are. So if the width is always going to be a natural and the height is always going to be a natural, and you multiply those two, this actually could be natural instead of number. And one of the things that we're going to talk about a lot in the course is that when you write the signature for a function, you always want to use the most specific types that are correct. Turns out it makes it much easier to think about using the function and to debug programs if you use the most specific correct type. So in this case, this function was never going to produce a floating point number like 3.2. It's always going to produce a natural, so we take the trouble to make the signature say that. And I'll save that file and run it one last time. The test passed.
Okay, so he put it in the same line, which is interesting. Yeah. I think that makes sense. Okay.
In this HTTF example problem, you're going to see a case where the problem statement isn't very specific about the function we need to design. That's going to happen more and more as we go forward in the course. Remember what I said in the first video. Design is the process of going from a poorly formed problem to a well-structured solution. So making the problem more specific is part of the design process. In this video, I'm also going to talk about how many tests you need for a function. And we'll see another example of a case where you get partway through the recipe and realize that you need to go back and refine some work that you did in an earlier step of the recipe. In this problem, we're asked to design a function that consumes an image and determines whether the image is tall. So let's see. It seems clear that it consumes an image. But what does it mean to determine whether the image is tall? Well, we're asking, is this image tall? So that's kind of a yes-no question. By convention, whenever we design a function that produces the answer to a yes, no, or true-false question, we design that function to produce a Boolean. So we'll say Boolean here. Okay? And now what's the purpose going to be? The purpose is going to be something about if the image is tall. And the key thing is, so far I've only said it produces a Boolean, but I haven't said what true means. So you want to say in the purpose, produce true if the image is tall. You need to distinguish which does true mean. Does true mean that it's tall or that it's not tall? So whenever you've got a function producing a Boolean, your purpose has to be very clear about what true means and by implication what false means. So let's see, here's a stub, and this didn't tell us what name of a function to use. The problem statement didn't tell us what name to use. That's usually going to be the case. You're usually going to have to invent the name of a function when you design it. And it turns out that in the programming language we're using, there's a convention that functions that produce a Boolean, functions that produce an answer to a yes-no question or a true-false question, have a name that ends in question mark. So we're going to call this function tall question mark. It's going to consume image, and a good dummy answer is false. So that would be the stub, and now we can write some tests. So let's see, check, expect, tall.
So check expect. How do you know if image is tall? If the image height is greater than the width, right? That's how you know it's tall. Check expect. Tall. Oh man, the syntax is I'll get used to it, but basically, okay, that's how you do it. Just copy that, cause no, that's right. Check expect tall. Man, tall takes an image. And then I'm just gonna put in like greater than 4 is greater than 2. I think so. Basically, I'm trying to say like. What I'm trying to say is 4 is going to be the height, and is that how I would test it? I'm not sure. And then the template then would be define tool image, and then we're gonna have to do something with the image. I think that's basically the template. This is cool. So his convention is to use double quotes for those, single quotes for stuff, not quotes but semicolon, for stuff that we may not need later on. Yeah, let's see. I think it's gonna be the last one. I'm gonna call it. It's been almost 2 hours here today. All right, so tool image. What do we want to do? We wanna. Okay, so now the actual thing is gonna be define tool image greater than if image height is greater than the image. So oh no, hang on. This is like, yeah, I mean, do I need to put like an if thing here? I forgot how you do the conditionals. Here, if yeah, true. I mean, it needs to be true or false. So like, let's see what it looks like. If tool image height is greater than image height of the image width of the image. So if this is true, then it's tall. Otherwise, I don't know, it's Boolean. We want true or false, right? Is this let's stop. We don't want to stop there. Yeah. Okay, it looks kind of ugly, but I guess it works.
Question mark. Let's see, I need an image, so let's take a rectangle. Oh, wait a minute, before I forget here, I'm using rectangle. So let me quickly go up top here and say require true http/image. So I'm going to make a rectangle that, let's say, is 2 wide and 3 high and is red. The color doesn't really matter here, but rectangle needs the arguments. Let's see, it seems to me the rectangle that's 3 high and 2 wide is tall, so we'll say true. Now I want you to ask yourself right now, how many tests does this function need? The right number of tests for functions is going to be an issue that we talk about more and more during the course. How many do you think this function needs?
Oh, we should have second test. I'm listening to the guy, right? So it'd be like a positive test. Well, pass test. Guess, is it positive, negative test? I don't know. So this would be like false is what we need. That will give us a false, right?
Write down your answer, or just remember it, and we'll see where we end up.
Oh, it has a video in 2 parts, I guess. Fine. How many tests? 2? 2, I mean? Submit? Can I submit? No. Show answer? Oh. 3. Oh, what if it doesn't have a height? Interesting.
For now, I'm just going to kind of assume that it only needs this one test. That won't turn out to be right, but we'll see what happens. Let me run the tests, and there's one test and it runs and fails, so it's well formed, so we can keep going. Let's see, this is the stub, we'll comment it out. We'll write the template is tall question mark img.
Oh yeah.
IMG. We'll make
Also, like this, the way this image is done. Yeah. Again, better to do, better do this. I think rectangle. How he has it too free. Solid, red. True. I guess with height. 3, 2. Yeah, this is way better than what I had. Let's move it here. So these sort of parse. That should still work. Expected a. Oh, this is annoying. I should pause now. Oh, what happened? No. Stop. What is this? I don't want this. Did I? Am I missing something here again? These parentheses are gonna kill me. No. What did I miss? Line 267. What? Oh, that's it. Okay. I think it was fine. It's just the way. Yeah, I think this is the right way. Yeah. Okay. Cool.
a copy of that.
What's okay? Hang on.
And
So we kind of cheated, right? There would be 3 answers. What would be the third test? Suppose, I guess if there's like a circle or something. And that would just be false, I guess. Three, but only 2 found. Okay. Okay, how the we have circles here before, no? 30, so okay, it needs thickness or something. What's 30? Or like the height or something? Yeah. A negative and like edge case test, I guess. I don't know if these things are
comment out.
how you'd call
The
it.
original template will label it as template. Let's see, these functions have 2 cases, right? Sometimes it's tall and sometimes it's not tall. So when you have 2 cases, you can use an if, because that'd be the case where it is tall and the case where it isn't. And what I like to do whenever I add an if to my template is I put in the if, and then I make myself 3 copies of the rest of the template as a way of saying, okay, now I've got the if in there, and I need to decide what happens here. Now let's see. Tall involves comparing the width to the height. So let's see. If the image height of the image is greater than the image width of the image, let's see, if that's true, then the image is tall, and so I should produce true. And otherwise, I should produce false. Well, let's try running that. Okay, the test passed. The test passed, but are we done? Have we really tested this function? Well, one clue that we haven't, Dr. Racket is giving us right here, in the way it's colored this false. Depending on how you have your Dr. Racket configured, it might actually just highlight this false with black. But in both cases, what it's saying is hey, this expression here was never evaluated. There's this concept called code coverage for a test, or test coverage, which says, given all my tests, how much of the code is actually being evaluated? And if the answer is not all of the code, then you don't have enough tests, because what if a piece of code that isn't evaluated is wrong? You haven't tested that piece of code. So whenever you run your tests, if you see code that's highlighted that says that it didn't get evaluated, then you know for sure you need more tests.
This could be
What's happening, of course, in
simplified.
this case is we tested the case.
How can you simplify this method? So define tool. I mean, because this was return true or false, no? Right? So I'm expecting whatever it is. Yeah, true. Okay, here's what I want to do. Like a bit of a duplication, but yeah, and then just want to test something. So, and if this is like 4, it should be true false. Yeah, so in that case, we don't need an if. We can just check if right. I don't know, maybe we can do this. It should still be the same. Yeah.
Where it is tall, but we didn't test the case where it isn't tall. In this case, we can do that fairly straightforwardly by copying the first test and just swapping these two around and saying, well, in that case, it's false. Now let's run it. Both tests pass. But are we really done? Let me give us a bit more room here. Are we really done? At this point, what you might think of is, hey, wait a minute. There's one more case. What if it's the image width and the height are the same? What should happen then? And this is a thing that happens in function and program design all the time. You realize partway through the design process that there's a boundary condition, or sometimes we call it a corner case, that you hadn't quite thought of. It's perfectly fine for that to happen, but when it happens, when you say to yourself, wait a minute, what if the width and height are the same? You need to immediately do a couple things. First, write an example for it. Then decide what the behavior is. And I'm going to decide in this case that if your width and height are the same, you're not tall. So write the example, write the expected result, fix the purpose. Height is greater than width. So that's unambiguous in the purpose. And
Yeah, very, very valid points, I think.
if what you decided required you to change the function, change the function. In this case, it didn't. But if I had decided this the other way, I would have to change that to a greater than or equal. And now run the test again. Now all 3 tests are passing. So that's the design of that function. That works. When I run it and the tests pass, all my code is evaluated, so I've got good test coverage. So I'm pretty good here. At this point, I just want to make one minor detail point, which is whenever you have an expression of the form if something, true, false, you can always replace that by just this simpler thing. You comment this one out. Bracket, comment out with semicolons. Why are these two the same? Well, look, this one says if this expression evaluates to true, then produce true. Otherwise, if this expression evaluates to false, then produce false. So that's really just the same as the expression itself. Either this expression evaluates to true or evaluates to false. So whenever you have if something, true, false, you can just replace it with the question itself. In a normal program, once you've done something like that, you would clean this up and delete that out from there. And in a couple weeks, you also won't leave the stubborn template behind.
Because I think I'm testing the same thing here as well. I want to see. Yeah. So this thing is the exact same thing. Height with height equals with oh, what? Okay. Oh, what else we got? Wrap up. Yeah, we wrap up. So what did we do today? Okay. Yeah, I'll probably do this like tomorrow or something. The problem bank, we go through the problem banks later on. How to design the function quiz. Yeah. What is this? Evaluation tutorial. Yeah, I don't want to do that. Evaluation tutorial. Yeah, I don't want to do that. I don't know what that is. Module wrap up. So that was that module 1. Yeah, that must have been. Yeah, okay, that must have been module 1. Of course. This is very. It's very difficult to navigate the thing. Okay, that was module 1A and 1B. Alright, so that's what we got on today. 1A and 1B. Yeah, I'm gonna end the stream here. I'll probably just tweet about this. And yeah, alright, catch y'all tomorrow. Bye. Let's stop the stream.